Our next speaker is Dick Manchester, who is going to talk about timing of pulsars.
So I'd like to tell you a bit about pulsar timing. It's obviously a key part of the science of pulsars. So I'll try to give a bit of an introduction and then go on to talk about some more recent results. So this is the observed period distribution for pulsars. There's currently about 2,600 pulsars known. Almost all of those are in the galaxy. There's 29 extragalactic pulsars, all of which are in the Magellanic Clouds. As is well known, the pulsars go into two groups, millisecond pulsars and normal pulsars. Most of the millisecond pulsars are binary, indicated by the blue colour, and many of the millisecond pulsars are in globular clusters. So I won't be talking about these source classes in this talk, but I will talk quite a bit about millisecond pulsars and normal pulsars. So this is the PP dot diagram. The lights are a bit bright to see it very well, but I think everybody's seen this before. The point here is that there's enormous diversity in the pulsar population. The millisecond pulsars live down here. Here are the normal pulsars, and up here we have the magnetars. And Sama Safihab will talk, when is it, Thursday morning, about the diversity of neutron stars, of pulsars. So there are these two basic properties, the characteristic age and the surface dipole field, which there are lines on here which you can't really see, which are lines of constant field and age. So we can measure pulsar periods to very high precision. So how do we actually do that? We first of all, when a pulsar is found, we have a basic period, and usually the dispersion measure sort of very approximate, but enough to average a certain amount of data together to form a mean pulse profile over half an hour or so. We then can cross-correlate that mean pulse profile with a standard template to give what's called the pulse time of arrival at the telescope. So that's the basic quantity of pulsar timing. And then we then measure a series of these TOAs over days and weeks and months and years. Because the Earth is a moving frame, it's rotating, it's going around the sun, we have to transfer these TOAs to an inertial frame, and we use the Solar System barycenter for that. So we then compare these barycentric TOAs with predicted values from a model for the pulsar. So the model for the pulsar includes its position, its the pulse frequency. If it's a binary, it includes all the binary parameters and so on. And the differences between the observed TOAs and the model TOAs are called timing residuals. So we then fit these observed timing residuals with functions that represent the errors in the model parameters. And so this shows the types of variations that you can see with different errors. So if the pulse frequency is wrong, then there's just a linear drift in time with the TOAs. And from the gradient of that, you can correct the pulse frequency. If the frequency derivative is wrong, you get a parabola. Because of the barycentric correction, the position of the pulsar matters, and if that's incorrect, you get an annual term as the Earth moves around the Sun. And from the phase and amplitude of that, you can correct the pulsar position and get very, very precise precisions. You can even measure proper motions and parallaxes. If the pulsar is binary, you get these complicated functions at the orbital period, which repeat at the orbital period. So by solving for all of, looking for these characteristic signatures in the timing residuals, you can improve the parameters of the pulsar. Once you've done that, if you then redo the timing fit and look at the residuals, they may just be white noise, which means you've got a really good model for the pulsar, but there may be some systematic trends in there, and they're the science. Now, pulsar timing is very powerful. This just lists some of the applications of pulsar timing. I'm not going to go through all of this list, but it just illustrates to you the power. Oh, what happened there? Damn. Is that back? Yeah. It illustrates to you the power of pulsar timing. So in this talk, I'll concentrate on some of these ones up at the top, and I won't have time to go through them all. Done. Is that back? Right. Okay, so pulsar braking, I'll say a few words about that. All pulsars slow down due to energy loss, either to magnetic dipole radiation, which are electromagnetic waves at the rotation frequency of the pulsar, or to relativistic particle winds. Because the pulsars are rotation powered, they're powered by rotational kinetic energy, losing energy causes the pulsar to slow down. There are some very interesting pulsars known as intermittent pulsars, where the pulse goes into what's called a null for a certain period of time. Several months in these cases. You do get shorter nulls as well. And then it comes back on. And in this important paper by Michael Kramer in 2006, they showed that the rate of slowdown of the pulsar was different when it was pulsing and when it wasn't pulsing. And that demonstrates clearly that the same currents are responsible for both the spin down of the pulsar and the radio emission. Now you can define a parameter called the braking index, which is related to the pulse frequency, its second derivative, and the first derivative squared, which is a diagnostic of the mechanism for the pulsar braking. If it's a pure magnetic dipole effect, then this braking index is equal to 3. But if it's if the braking is largely due to stellar winds, then the braking index is less than 3. And the direct measurement of this braking index for a few young pulsars generally gives values that are somewhat less than 3. So that's consistent with the particle wind contributing to braking. Unfortunately, it's impossible to measure the braking index for millisecond pulsars. This new dot term on the bottom line here is just too small, and so it's just not possible to measure the braking index. very strange going on here. I can't move on. No. I'll try again. Okay. Most of you will know about glitches. These are sudden spin-ups in the pulse frequency. There have been 425 glitches observed in 141 pulsars. That's at least according to our ATNF catalogue list. The spin-up is generally between 10 to the minus 10. In fact, there could be a lot of glitches less than that. That's really an observational limit. And the biggest ones known are about 3 by 10 to the minus 5. This is for spin-powered pulsars. There's been a recent paper for an accretion-powered long-period pulsar, 1,000-second period, which has a bigger delta nu over nu than this. An important diagnostic of what's going on is the amount of change in the spin-down rate, and that's generally about 10 to the minus 3 for the larger glitches. It's hard to measure for the smaller glitches. It's found that there are typically a combination of exponential and linear decays back toward the equilibrium state. So this is an exponential initial decay here in the frequency derivative, and then it tends to be a more linear function. So in a recent paper, Espinosa and Andrew Line and others fitted a template to these exponential plus linear decays, the first part of that. And they see an increasing trend in this sort of central point of this template. And from that, they can compute a breaking index. And they obtained these values, which are all considerably less than 3. And in particular for Vela, this is a Vela pulsar, they get 1.7 plus or minus 0.2. So that's unusual, or maybe unexpected, and it's maybe also a bit controversial. I was just reading today or yesterday about looking through ADS, and I came across this paper by Akbal and Ali Alpar and colleagues, where they use a somewhat different method of taking nu dot just before the glitch, and they get for Vela 2.81 plus or minus 0.12, which is very different to this, completely different, well outside the combined uncertainties. So I think there's a lot yet that we don't understand about what's going on here. This is quite a conventional value, whereas this is an unusual value. Okay, so that's all I had planned to say about glitches. I've lost track of time now that I had to restart that, so 7 minutes. Oh, gee. Okay, so I'll have to rush. So you've all heard of the Hulse-Taylor binary, so I won't dwell on that. The important point here is that by measuring 2 of these post-Keplerian parameters in GR, these are just dependent on the masses of the pulsar and the companion. So once you've measured these 2, you can compute the pulsar masses. Then you can then predict what the third relativistic effect, the orbital period decay, should be, and thereby test general relativity. And this is a well-known figure for this prediction of the orbital decay in the Hulse-Taylor binary, and GR predicts it precisely. So this was not only a confirmation of general relativity, but it was the first observational evidence for gravitational waves, because that gravitational waves is the energy loss process that causes the orbit to decay. So that's a very famous result. Just going on to the double pulsar, which we discovered at Parkes back in the early 2000s. It has an even shorter orbital period than the Hulse-Taylor one, and so these relativistic effects are even bigger. We published results in 2006 where we had a total of 5 relativistic terms. We're now updating that, and so there's a total of 6. This is the so-called mass-mass diagram, which is quite complicated and busy, but the important point here is that these various relativistic terms all imply allowed regions on this diagram. And if the theory of gravity that you use is a good one, then there should be a region on this diagram where there are 2 masses which are consistent with all of these constraints. And if this is a blow up of this central part and there's a tiny little region there which is consistent with all the constraints. So that means general relativity is accurately describing this, this system. And we now have the best measurement of the orbital period decay, which is an order of magnitude better than the measurement in the Hulse-Taylor system now, and to 0.02%, and it's fully consistent with the GR limit. I was going to say a little bit about other tests of gravitational theories. I mean, GR is not the only theory of gravity. So in principle, you can use pulsars to place, well, not only in principle, in practice, you can limit the parameters of other theories of gravity. Since I'm running out of time, I might have to skip this. This is the pulsar triple system, and there's a talk actually this afternoon by one of Jason's students or postdoc, I'm not sure, about this system, so I won't say too much about it. The reason I put it in was that there is the potential with this system of providing a very sensitive test of the strong equivalence principle. There's an effect where if the system is in an external gravitational field, it will induce an eccentricity in the orbit, and that's usually tested by the gravitational field of the galaxy, but here you can actually test it with the gravitational field of the second outer planet, and it's potentially much more sensitive. So moving on to pulsar timing arrays. Pulsar timing arrays are arrays of millisecond pulsars which are spread across the sky. And in principle, you can detect gravitational waves and other effects with these pulsar timing arrays. We all know, of course, that gravitational waves have now been detected by LIGO. It's a fantastic result, and not only have they found this one, the first one, but there are now 3 others, which are quite surprisingly are all double black hole systems, no double neutron stars yet. But I just wanted to point out that in terms of tests of general relativity, the double pulsar is still a far better test at the low orders. There's a confusing way they labelled the post-Newtonian orders in the GW community, but this 0 term is actually the the first gravitational radiation term, which goes as V upon c to the fifth. And the double pulsar test is, what, nearly 4 orders of magnitude better than the test from the GWB. And even the second term, which goes as V upon c to the sixth, the double pulsar gives a better limit. After that, the GWB gives a better limit because V upon c for the double pulsar is relatively small, only 0.002, whereas it's of order 1 for the GWB. So getting back to pulsar timing arrays, in principle, we can detect several different effects with these. What we're looking for is a signal in the different pulsars which is correlated between the different pulsars. So that means it's not just related to one pulsar. And we can detect clock errors. So if all of the pulsars are speeding up or slowing down together, that's not due to the pulsars themselves. It has to be due to something here on Earth. And the most likely effect is an error in your in the reference timescale. If you think of that in terms of distribution on the sky, that is a monopole signature. We use the solar system ephemeris to convert to the barycenter. If that's in error, that basically means the Earth's not where we think it is, and so pulsars over here will arrive a bit early, pulsars over here will arrive a bit late, so that's a dipole signature. And gravitational waves have a quadrupolar signature, which is illustrated by this famous Hellings and Downs curve. So in principle, we can separate all these things. There are 3 major pulsar timing arrays around the world: the European, North American, and the Parkes one. At the moment, we've only been able to limit the strength of a gravitational wave background at the very low frequencies that these pulsar timing arrays are sensitive to, in the nanohertz band. And that's disappointing in a way, but it's also quite interesting because we're now ruling out most of the standard models for the formation and evolution of galaxies and the supermassive black holes in their cores. So some of the assumptions that went into the predictions for these models, for the amplitude of the gravitational wave background, must be wrong. And it could be the black hole mass function, or it could be the merger rate, or it could be other things. We would, of course, like to detect gravitational waves with a pulsar timing array. And the best way to do that, it turns out, is to increase the number of pulsars in the array. So the first step in doing that is to form the International Pulsar Timing Array and combine the data sets from the 3 national or regional PTAs. So we've now done that, and we're working on those data sets. In the future, we expect China with FAST and the QTT in Xinjiang to contribute to the pulsar timing array effort, and South Africa with Meerkat, and ultimately SKA-1. So there'll be many more observations of many more pulsars. We could even have hundreds of pulsars in a PTA, and with that we think we're almost certain to detect these gravitational waves and in fact be able to study them. I'll just say a few words about the pulsar-based timescale. I mentioned that if the reference clock is irregular, then you would expect to see this effect in all of the pulsars. So that's what we're doing here. We're searching for so-called common mode signal that's affecting all of the pulsars in the same way. And so with that, we can potentially establish a pulsar timescale which is based on the pulsars. And to do that, we sort of invert the usual problem of timing the pulsars with respect to the reference clock. We turn it around and we time the reference clock with respect to the pulsars. And that defines this pulsar timescale, which is independent of Earth-based timescales. It's based on the pulsars, which are way out there. It's based on completely different physics. Atomic clocks are based on quantum mechanics. A pulsar timescale is based on rotation of a macroscopic object. And importantly, the pulsar timescale will continue for billions of years. Atomic clocks only last 10 or 20 years, and then they have to replace them. So there's potential for errors to creep in on that, but the pulsar timescale will keep going forever, basically. So this shows our latest results on this. I probably don't have time to explain it in detail, but the important point is up here, where we're timing, looking for a common signal with respect to International Atomic Time. Now, International Atomic Time is known to have errors in it, and there's an improved timescale called TTBIPM 15, and this red line is the difference between those two timescales. And you can see that the pulsar timescale, which is this blue line, and also these points with error bars for two independent analysis methods, do in fact follow the difference between BIPM 15 and TAI. So that's quite important, because that shows, first of all, that TTBIPM 15 is a more stable timescale than International Atomic Time. The clock people believed that it was, but they didn't really know for sure, and we've now proved that. And it also shows that the low frequency, long-term low frequency stability of the pulsar timescale is comparable to that of the best atomic timescales. So finally, just a little bit about spacecraft navigation. Pulsars can form effectively a GPS system for navigation in space. GPS is used, everybody has it on their mobile phone, and that's based on satellites going around the Earth. But if you're in a spacecraft halfway to Mars or something, that's not much use to you. But you can, in fact, use the pulsars as beacons and solve the timing equations for the position of the spacecraft. Normally, when we're doing pulsar timing, we put in the position of the observatory, and then we solve for the pulsar parameters. But again, you can invert that problem and use the pulsar timing parameters as input and solve for the position of the observatory, which in this case would be some space probe. So China's actually launched a satellite called XPNav, which is exploring this idea. So there's a lot of interest in this. So pulsar timing has got many, many possible applications in physics and astrophysics, and it often provides quite unique results and insights into these topics. I've only just really skimmed the surface of just a few of the possibilities that you can analyze with pulsar timing. And there's lots of, or quite a few new and large radio telescopes coming online soon, so the future for pulsar timing is quite bright. I'll stop there, thank you.
Ali?
Dick, I'd like to comment on the breaking indices. This recent paper we published with Onur Akbal, who's here. When you try to find the breaking index, the problem is to extract internal effects of the neutron star, the response to the previous glitch. And as you pointed out, there are exponentially relaxing effects, and then there are long-term power law behavior. Now, what was done in the earlier papers was to take a fiducial time, which was a certain time, like 150 days in the case of the Vela pulsar, after the glitch, which is fine for exponential relaxation because you are sure that it's over by that time. But when you have power law behavior, as you showed there is, then you have to wait as long as possible and compare the amplitude of that term with the way it's relaxing, and then you choose the fiducial phase just before the next glitch. And when you do that, then we obtained for the Vela pulsar 2.8.
Yeah, I haven't had time to read your paper yet, but clearly there are quite different results being obtained from these two different methods, and so it needs to be sorted out.
Matthew?
Dick, so back on the glitches again, you've highlighted three prominent cases where we have very good data monitoring, and they all show exponential with subsequent linear recovery. Do we have any sources that buck that trend, have a different type character in terms of the recovery history?
Yeah, well, there are some where these trends are not so clear. I think, often, you know, for small glitches, you can't resolve these things. It's you just don't have the sensitivity. It does seem to me that most large glitches, this is a pretty characteristic sort of behaviour. But you know, the pulsar glitches, there's a whole zoo of them, and you know, the crab, for example, is quite different. There seem to be the sort of Vela class glitches all seem to behave in this way, but other glitches, maybe smaller ones, do seem to have different properties. So it's not universal. I think it's a very complicated phenomenology on these things, but at least this characteristic exponential plus linear does seem to be quite, it's present in most of the strongly glitching pulsars.
We must move on, so let's thank again Dick. And the next